Here's all a gas really is, a box of tiny molecules, flying around and bouncing off the walls. Everything you measure about a gas is just this motion, seen from far away. Watch three things fall out of it. First, how many are crammed in? Pack more in, and the gas is denser. That crowding is the density, call it rho, painted gold. Second, how fast they jitter. This blue arrow is one molecule's speed, c. The faster they fly on average, the hotter the gas. That jiggle speed is the temperature, T, in orange, on the thermometer. Third, the good one, watch the right wall. Every molecule that slams it makes it flinch. One hit is a tap, but thousands a second blur into a steady push. That drumbeat is the pressure, P, in red. So here's the puzzle. Each molecule is just a point going straight until it hits something, no plan, no order. Where does a smooth, steady pressure come from? And how could it possibly know the temperature? Let's build the link. It collapses to one clean line. This equation sits at the very start of the subject, get it, and the gas's energy, its flow, and its momentum all follow. Let's build it, straight from the molecules. Take one molecule. Its speed splits three ways, along x, along y, along z. Three directions to move in. Which part pushes the right wall? Only the one aimed at it, x. The other two just slide along. One direction in three does the pushing, that's where the 1/3 comes from. And when we write that push as energy, 1/2 mv squared, an extra factor of 2 pops out. 1/3 from geometry, times 2 from the energy, makes 2/3. Add up every molecule's kick on the wall, that's kinetic theory, and out drops this, pressure times volume equals 2/3 of the molecule's total motion energy. Second fact, the heart of it. Temperature just is the average kinetic energy of one molecule. Each direction carries 1/2 kBt, so the average of 1/2 mv squared is 3/2 kBt, kb. Boltzmann's constant is the tiny number turning jiggle energy in 2 degrees. And watch, hotter means faster. Now collide them. Drop the temperature line into the wall result, and pressure times volume becomes 2/3, times 3/2, times n kBt. Watch the two fractions. Over 1 bar, 2 times 3, over 3 times 2. Strike the 2's, strike the 3's. 6 over 6, exactly 1. Not roughly, exactly. The whole coefficient is gone. So the equation of state is just pressure times volume equals n kBt. A common trap is to drag the 2/3 along and write 2/3 n kBt, wrong. It was already eaten by the 3/2. The same law wears different outfits. Count molecules, n kBt, bundle into moles, the universal Ru, weigh it in kilograms, mRt, with a new constant R per kilogram, its PV equals RT, and flipping specific volume for density gives the form we live in for the rest of the course, pressure equals rho RT. But which R is that? Here's the split that trips everyone up. There are two, and they're not the same number. Ru, the universal one, is 8.314 joules per mole per Kelvin, the same for every gas. The specific R, no subscript, is Ru divided by the gas's molar mass, for air, 287 joules per kilogram per Kelvin. Universal per mole, specific per kilogram. Mix them up and every number comes out wrong. Put it to work. A rigid 30 cubic meter tank, we pump air in at 1 kilogram a second, a cooler holds 300 Kelvin. How fast does pressure rise? Differentiate the state law at fixed volume and temperature, the pressure rate is mass flow times RT, over the volume. Feed in the numbers, 1 times 287, times 300, over 30, and it lands on 2,870 pascals per second. Anderson prints 2867 with a slightly rounded R, same answer. A concrete number, straight from the state law. What does P equals rho RT look like? Density across, pressure up, at fixed temperature, a straight line through the origin. Twice the density, exactly twice the pressure. The slope is A times T, the temperature itself. The tilt is the temperature, the height at any density is the pressure. Sea level air sits about here. Heat it, double the temperature. Molecules fly faster, hammer harder, and the line tips steeper, twice the slope, twice the pressure at the same density. The whole gas law is just this line, tilting. Back to the puzzle. Steady pressure from random points, just molecular impacts, averaged. And temperature, just the mean energy of that motion. The gas law is those two truths multiplied together. One honest warning. The perfect gas assumes point particles that ignore each other. Squeeze to very high pressure and they start to feel one another. And in the searing heat behind a strong shock, air dissociates and this clean law fails, which is exactly where we are headed next.